Good afternoon from Maine, or the woods of Maine, where it is currently 12 degrees and it is bright and sunny, and it snowed yesterday and we got about, I don't know, 5 inches. Um, anyway, it's 22 degrees out, and figured this is a good time to continue this lecture. We left off at the Ediacaran biota, and this is, as I said earlier in the previous lecture, the Ediacaran life forms are unique in the sense that although they're multi-celled organisms, they are multi-celled organisms that are more or less stacked. They aren't necessarily all different types of cells, although there are some, but they are not in the sense that we see today. In other words, they don't have a digestive tract, they don't have any foreseeable, pardon the pun, eyes or ears, nostrils, breathing apparatus. Most of them don't even have symmetry, or rather, there's no front or back. But they're a big jump from the multi-cell organisms that are eukaryotes, because the eukaryotes are essentially remain microscopic for the most part, with the exception of the stromatolites, and some bacterias and algae. But these are actual. They look like ferns, or they look like star fruits, or whatever. They do resemble life forms, but they definitely are not necessarily directly related. There are even these species, as we call them, the Ediacaran biota. They precede the Cambrian explosion, which is going to be another 20 million years after this. And they have the characteristics of some animal traits. And so we kind of are leaning towards the fact that there may be one or two species of these Ediacaran biota that are, in fact, animal. And I don't know if I've got any slides for that in this. However, we're going to see in a second here. But they're fascinating. And oddly enough, they lasted for quite a while in the Ediacaran, and then they went extinct. And then all of a sudden, boom, then the Cambrian explosion shows up. Although in recent times, there seems to be some links to possible a linkage to arthropoda. There are a couple of Ediacaran fossils that do resemble trilobites, so maybe that evolved into that. And there are some that may have evolved into echinoderms, which are like your sea urchins, and then maybe even some jellyfish. But in any case, these organisms, although they look like plants, they are not. They were very loose. They were liquid in form. If you were to take them out of the water, they likely would just flatten out like a jellyfish. So they really didn't have any bony texture or whatsoever to them. They are just more or less just cells combined together to make things that will float or be attached to the floor of the ocean. And one other interesting fact is that we don't think that these survived off of sunlight. So they were thought to be down below into the benthic zone where there isn't any sunlight. So they must have used some other form of energy, probably near hydrothermal vents, and using sulfur from that or some other form of energy. All right, this is another Ediacaran artist, idea of it. I don't know the names of these, but I do know that this is something called a Dickinsonia, and these are what we think are the first animals, or so far we've confirmed more or less that these, if there's any one of these that resembles an animal, it's going to be the Dickinsonia, and it may have even been predatory rather. We know that because there's when you get really down to the nitty-gritty and you want to find out what something is made of or where it came from, or you can break it down into literally almost subatomic particles, and once you do that, you can see things, residuals of things that converted during fossilification or whatever, even though these aren't fossils. These are imprints They had no hard parts, so they only made imprints. Basically, they died. Some sort of sandy, silty material came over them, and then compressed, and the shape of the animal was left over as a residual form in the soil that became hard. So, literally, when you look at a fossil of these, you're looking at the actual cast of it, I guess you would be. You're not really seeing. You're seeing what the animal looked like from the surface, but you're actually looking anything you're looking at, you're looking down. It's weird. In any case, the really high level electron X-ray machines. They'll break these things down, and they'll look at the spectra, rare earths, all sorts of stuff. But what they did find is that there's a mineral in here that can only be a residual, or basically a derivative of cholesterol. And cholesterol is only found in animals, so that's pretty good evidence that that may have been an animal. All right, here we are to the Cambrian period. And this is sort of where our story gets interesting. We are now going to start to build the area of New England and Maine and the east coast of North America. And this is how it kind of, so after a very long time in Earth's history, we've gone through 3/4 of time. We are now at 541 million years ago. The Cambrian explosion is basically means this is named after a formation in, I believe, England. And this is a time when life just explodes. Almost every single early example of most of the phylums that we see today, whether it be a mammal, or rather, you go back to that would have been, some sort of a primitive fish-like creature or worm. That would be more or less our lineage. The arthropod exists in the form of sea floor dwelling crustaceans. You have the bacteria, the algae, you got the sponges, you've got cephalopods. You've got almost echinoderms. You've got most everything ready represented here. That all of a sudden it just explodes about 541 million years ago. And that's just a coincidence that this one happens to say 514. This is the Earth at 514, but this period begins at 541 million years ago. So this is, 40 million years into it, more or less. So you've got a rift zone. A very, very large subduction zone on the western and northern part of the of the continent of Laurentia, which is North America. It is being pulled this way. So you've had spreading centers here, here, and here, and this is the Iapetus Ocean. Maine is right here on this red dot. So we've got a big giant ocean between us and Baltica, and somewhere down here is South America. Oh yeah, here it is right here. And there's a giant circumnavigating subduction zone that runs along the southern, a big portion, or at least half of the southern part of the globe. And this is pulling Siberia and Baltica down south and going under Gondwana. So we have a very passive margin, and it is very likely that this passive margin right here is what gave life the chance to explode, because we came out of a glaciation, a worldwide glaciation, a number of them in the late Neoproterozoic, and then tectonics calmed down. We have one of our first well-known passive margins where the water is beautiful. It's near the equator. There's all sorts of sunlight, and life really begins to take off, and that's where it starts. This is one of the reasons why so much evolution happened in such a short period of time. The conditions are ideal for it. This is the Cambrian period, or Laurentia, North America again, 510 million years ago. And what we have here is we have an island arc that has formed off somewhere off. This isn't necessarily depictive of where it would be. It's just showing you that it's somewhere between the Gondwana subcontinent and Laurentia, and then somewhere within the Iapetus Ocean. We are more and more trying to figure this out. But anyways, Subduction opened up to the southeast rather, and built up some island arcs here. And it is these island arcs that are going to weld on and accrete into eastern North America in another 30 million years. That will become the Green Mountains of Vermont. And 500 million years now, the arc is getting closer. Subduction is going under here. There's a mountain range. They are deposit. There's a trench right here, and this whole trench is going to close. And 485 million years ago, global view, you see the Taconic Islands. These are going to become the Taconic Mountains as they accrete onto North America. There's Maine right there, Siberia, Baltica, and of course we have Gondwana down here and the Iapetus Ocean right here, and Maine right there. It's interesting to note that, here is the equator. We are very far below, we're south of the equator. We are facing dead south. And in order to get to where we are today, this continent really needs to rotate about 90 degrees, and that's quite a feat to roll this amount of land 90 degrees in the next 500 million years. Because remember, these move at the pace that your nails grow. All right, so Cambrian tectonic and paleogeography map. 495 million years ago, as we said, we are facing dead south. We have the equator right here. We are east coast is below the equator, west coast is above the equator, and this is sort of what's happening. We have the Appalachian Seaway right here. This is open ocean. You got shale kind of depositing, deeper deposits. You have a shallow epiperic sea. So you have, sands, corals, massive reefs. They're probably gigantic reef system. Probably a lot like the Bahamas, but on a much larger scale. And tectonically, we have gone. The Granville orogeny came and went. It came, it went. We pulled apart. Amazonia disappeared. We had our passive margin right now, where life is really beginning to take off. Now we've got a subduction zone off to the well, in our particular orientation, off to the east, east-southeast of the present-day East Coast, and it has built an island arc. And as this plate begins to subduct into the into the mantle, it is going to just pull this chunk right over it and slam it into North America, which is here, and that is represented by this actual representation right here. But right now we're here and we are moving towards here. So timeline chart, pre-Taconic orogeny, about 480s when this baby starts up, and there it is right there, and we are getting very close. So we are about to close the Taconic Seaway. That's just the ocean between that arc and Laurentia. So we are right about here. This is the Cambrian life. As I said, it really, we have a lot of the food groups represented here, I guess. I don't know why I said that, but it seems to work. Anyway, you've got your arthropoda here. This is represented by the trilobites, which are just an incredibly successful life species. You just can't get any more successful, I think, than the trilobites for your bang for your buck. They're diverse. They're everywhere. They survived a good portion of when's the extinction event? 250 million years, and they survived all sorts of they survived some extinctions. They survived changes in climate. Sea level drops, volcanic eruptions, lip episodes, meteorite impacts, and they just survived and they evolved. You've got sponges right here. You've got corals right here. You've got your jellyfish, sort of probably echinoderm-ish sort of things. I'm not sure what these are. I think I do, but it's shadowed, so let's just say that I might know what they are. But I'm a geologist, not a botanist or a biologist, so I can get away with that. I don't have to know them all. This guy right here, you did not want to encounter. This is sort of a good example of your first predator You didn't want to encounter this. This guy's looking for these and or this probably, and it will just take apart anything that it comes in contact with. Um, Again, I apologize. I don't know the name of that. I want to say it's not the sea scorpion. It could. I don't know. Anyways, it's a freaky looking thing, and I believe it was probably about 3 feet long, if I'm not mistaken. So, yeah, stay away from that. All right, so now we are going to start the Appalachian orogeny. It's my math here, 380, 280, 230 million year orogeny. Um, and it is known worldwide. It is one of the major mountain belts built over the Earth's history. You don't just find it here. The Appalachian orogeny extends down into obviously the Ozarks. It goes down into South America along not the Colombian, the Belize coast. Basically, the northeastern part of the entire part, the north and eastern part of South America, pretty much is part of the Appalachian orogeny in some form. No, 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 no. I apologize. That is not part of the Appalachian orogeny because that actually had closed prior. So I apologize for that. Let's just call it at the northern part of South America, north and northeastern part. You also have the northwestern part of Africa. You have up through Greenland, although they refer to it as the Caledonian, but really it's the same. It's the same event. And you also have our European counterpart. Part of it residuals in Spain, France. But not much. Most of you're going to find most of the mountain building events would have been in England, Norway, Ireland, Scotland. They were all part of it as well. So, big mountain range, very important, one of our most studied, and it really understanding the Appalachian mountain range has allowed us to understand a lot more than about other mountain ranges around the world. It is a classic Wilson cycle event, represented by a minimal of at least 3 island arc episodes, and a microcontinent. So you have at least a couple of island arcs. Then you have Avalonia, which is a microcontinent that splits off of northwestern part of Gondwana, but it's actually the very top part, the northern part of northeastern part of South America. So that's kind of interesting, and I'm going to explain that in a little bit. And then you have Meguma, which is basically the outer part of it. So you got the island arcs here of the Taconic. You've got the closing of the Iapetus Ocean that takes this area right here, and then this area out here represents Avalonia, the microcontinent, and then you have Meguma, which is a piece of continental crust behind that. And all of this comes together to make this gigantic mountain range, which is basically highlighted in blue here. And this is sort of the line in the mountains, if you will, of how far it extended back. And that's anything beyond that we would essentially consider Grenvillian terrain. So even though these mountains were giant, both of these ranges are huge. Remember, they've been cut down into, and we're looking at the guts of the mountain ranges now. So what we're seeing is no longer the mountains of themselves. We're just seeing the guts of it. So imagine taking a phone book and crunching it together and then whacking it, and then taking it and just planing it right across, maybe, well, I don't know, maybe just 3 or 4 inches above the cover, and you would get pages. So if you crunch the book, you would get these pages. When you cut the top off, and you would just see the inner parts and the folds that made the pages of the actual phone book. That makes any sense. All right, so the simplified view of a continental collision is, and at least of what we're looking at is, you have an arc that's offshore. The arc ends up getting dragged into. You have an arc offshore of subduction. The arc more or less pulls this piece of crust right here this way, or sometimes this piece of crust will pull down and pull this. Either way, these two are in a collision course, and you have the island arc made of mostly intermediate to felsic volcanic materials made from the melting of this slab, punching up through this slab, and they pile, and you get an island arc. This is the oceanic crust, this is the open ocean floor, and then this is the continent right here. And these are going to slam into each other. What happens is this is this all right here is this, and this is that. And all of this has come together, and you've got a mountain range that consists of smashed ocean sediments, some oceanic crust, some deformed continental crust, and a deformed island arc. And eventually this is all going to get cut, at least in New England, and we see the guts of it that are here, here, and in here, and in here. So let's just say that this was, this right here was 6 miles higher than where we are today. So in other words, 6 miles of this is gone, and we would make a line like that, and that's what we see today. Eventually, sometimes, and more often than not, I guess, the oceanic crust that's being dropped down will break off. And when this does, you actually have a rebound effect sometimes here, and that may explain why the Appalachians have been rebounding in the last 30 million years or so. But in a continent-continent collision, when these, let's just find, because there is another piece of continent that's over here somewhere out of sight, eventually these two continents will collide, and you get basically something like a Himalayan-style mountain range, and eventually these two pieces are going to just run out of juice, and then they're going to start to pull apart. And once they do, you're going to get all this weight that accumulated that's holding down this very hot area of mantle is going to get released, kind of like shaking a Coke bottle and loosening the cap, and you're going to start to get fizz down here. And more or less, when I say fizz, I mean we're going to get melting from decompressional melting, and it's going to start forcing these two pieces apart. And eventually, you're going to get these pieces that move apart, and you're going to get new ocean crust forming. This is continental crust, this is ocean crust. And you have upwelling of very mafic magma that's driving these pieces apart. So that's a simplified view of a continental collision, and then the rifting event. That is a Wilson cycle. And so the Taconic Orogeny as represented on the Wilson cycle is this area right here. Remember, we kind of started here, we came down, we split apart. We have the very wide Atlantic Ocean, or the Iapetus Ocean rather. So yeah, Grenville Orogeny, Grenville rifts, continent becomes stable, there's rifting, the Iapetus Ocean opens, we have the Iapetus Ocean, and now we're starting to close it. And just imagine you're looking south, Florida is up here, or down here rather, and this is Vermont, and we're getting a whole bunch of subduction going under here, and this is coming together, and we're going to be getting mountain ranges, and this is going to weld on to the continent. Does that make sense? If I'm looking, yes. Well, actually, no. Anyway, and eventually this will close and we'll be over here again. So the arc would be offshore. Yeah. Yes, correct. Just know that this is just a character sketch of what is going on. The stage that is set for the offshore island arc of the tectonics to slam into. What we're looking at is this. We're looking north. This would be the offshore island arc. It is subducting. You have subduction here. This would be North America. This is the offshore arc, and the arc is going to slam into here. Apologize for that. I just kind of got confused, as I often do. So the cross-section of the tectonic events, we are now represented here. I had to put in my own little thing. This is my own sketch, by the way. And you have oceanic crust creating an island arc, and this arc is going to go in. So these are the Taconic Mountains, and they are going to weld right onto here and close this little Taconic Seaway right here. This is another sketch that sort of illustrates it in slightly more detail. Volcanic arc, Taconic Seaway. So Iapetus Ocean, we have the volcanic arc offshore. You have a narrow seaway that's becoming narrower between the arc and we'll just say western Vermont, western Vermont or eastern New York. This is a reef that's actually going to get between the arc and we'll just say eastern New York. And this is the area of the Green Mountains. We have a huge area of nice wide open ocean, and what's happening is this huge amounts of carbonates have formed, like in the forms of reefs. And what's going to happen is these are going to get smashed and compressed and turned into marbles. And if you ever go from, Connecticut, Western Mass, and through Vermont up into Canada, there is a huge area of marble that goes right north-south along the western margin of Vermont, and that is from this crunching this and making a marble out of the reefs. So here we are at 543. I'm sorry, 500, and the 500 million year, the arc has grown, it's gotten bigger, it is now scraping up the ocean sediments, which is in the form of reefs right now. They are compacting, they're getting driven onto North America. And finally, subduction is now complete. The arc has been driven up onto, we'll just call these are the Green Mountains right here. This is New York right here. New Hampshire would be here. Maine hasn't really formed that much yet. Maybe the northwestern parts of it. But this is the first suture on the east coast, and there'll be a couple more coming behind it. So now a part of the Iapetus Ocean has closed, and we have all these right in here have been this area right here, all that reef has now turned into marbles. And this is the closure of the Iapetus Ocean. So we just went through the Taconic Orogeny, which is more or less represented right about here. This is a very complicated diagram. It's something that really somebody deep into geology is gonna really appreciate. I do, because it explains everything. But the gist of it is, let's just imagine we're near Montpelier or something, or somewhere in central Vermont, right here, and then this over here would be the continental shelf, straight east. We'll just go east southeast. So we'll just say somewhere at the furthest point of the continental shelf off of Massachusetts. So just imagine a line from sort of more or less Montpelier, Vermont to, we'll just say somewhere off the coast of somewhere off the coast of Newburyport. Go out about 600 miles to the continent, to the edge of the continent, and that would be it. So Montpelier, 600 miles east of Newburyport, Mass. And what you have at 520 to 505 is you have a series of things that are coming together. And you have essentially the ocean is here. You have an island arc here. You have a seaway that was here. And then you have another volcanic island arc here, and then you have Ganderia over here, which is a microcontinent that came off of north, east, South America. And if you look at that slice of the Earth, this is what you're going to see. And this is before it happened. This is just basically saying, this is just showing how everything kind of occurred. This would be the beginning. Literally, what it doesn't show is water would be covering most of this right here. But you have a subduction zone here, creating this arc. You did have a subduction zone here that kind of built up this arc. And you have a piece of north part of Amazonia, basically, that got ripped off when this subduction over here started. So you fast forward to 480 million years ago. This area right here, which is the seaway between the island arc, that's going to be the Taconic mountains. This is the seaway. This is the volcanic arc that's going to become the Green Mountains. This ends up slamming it and closing the Taconic Seaway right here. It's going to thrust up onto the west coast, the east coast of North America. This first arc is going to get slammed up on here as well. Subduction continues here. The Iapetus Ocean begins to close. This is being drawn this way, and you actually have an opening right here now. So you have more oceanic crust filling here, but now you have more subduction over here, and it's beginning to pull more pieces of Amazonia, or maybe even Africa, off at this point. You fast forward from 480 to 470. The seaway is essentially gone. You have thrusting here. Actually, I apologize. The Taconic Seaway is not gone yet. This is the beginning of thrusting, so it's closing. It's closing here. It's closing here. It is not closed until we're down here. I apologize for that. So the row, we'll just call this the Green Mountain Arc, but it's known as the row belt. Basically gets slammed onto here. It closes this gap, which is the Taconic Seaway. Subduction continues here. Mooretown. And the Shelburne Falls arc begin to get pushed over here, and you have a thrust fault forming here. So you have the row belt getting essentially thrust faulted, broken in half, and it's getting thrust on itself. You have subduction continuing here. You have an opening right here due to the subduction here. Subduction continues here. Ganderia now, that would be going, oh yes, because subduction here, Ganderia is actually being thrusted, and now we have the Rheic Ocean forming. So you have Iapetus, Ganderia, and then you have the Rheic Ocean here. We go to 460 million years ago. The Taconic Mountains have been built. The seaway has been closed. This is the sediments that were on the seaway. So you have North America continent. You have Grenville stuff on top of that. You have the sediments from the Taconic Seaway smashed here. You have the Shelburne Falls arc, the Mooretown arc. They're all thrust up on each other now because everything's being driven this way. The slab that was underneath the Shelburne Falls arc is now broken off. You have intrusions here. You have more granitic intrusions here. This area here, subduction still continues, and you are pulling Ganderia right here. Well, they call it the Victoria Exploits back arc, but this is really part of Ganderia here, and it's being pulled this way, and it's eventually going to contact this area right here. And you also have subduction starting on this side right here. Now we fast forward down to 445 million years. Taconic mountains have been built. The whole thing has been slammed into each other. You've got the arcs on top of arcs on top of arcs. You have in the back area the arcs being broken within themselves and thrust upon themselves. You have the closure of the Taconic Seaway. You have subduction here of parts of Ganderia getting subducted under the island arc system of the Taconic Orogeny. You have all sorts of plutonic activity going on in here. from subduction and melting of slabs. You have subduction now coming in from to the west, going underneath Ganderia here. You have Avalonia, the microcontinent that broke off of northern Africa on its way. Where earlier, I believe I said that Avalonia came off of northern Amazonia or South America. That's not entirely true. Ganderia, we think, did. Avalonia might have been a little bit more west because at the time, South America, northern South America and northern Africa were connected. So we think that this is more of a northern Africa terrain, so I apologize for that. This is my first time doing these videos, so there's going to be mistakes, but I promise I will continue. So anyways, this is really this is a very, very detailed description of the building of New England. I mean, this is it. This is everything right here. We don't have anything more than Avalonia sticking out on the eastern part of New England to the end of the continent, and to the west, obviously, we don't go any further than North America itself, and that is represented right here. And in between, we have arcs. We have the closure of an ocean. We have a microcontinent that closed another part of an ocean called the Rheic Ocean, and everything is all crunched together. We have all sorts of plutonism and plutons, granitic plutons like this, and gabbros and what have you. When you have plutonism from this, due to the subduction and the compression, this kind of stitches everything together and keeps it together. So very complicated. I hope when I do this the next time I can make this a little more simple, but this is the true. If you look in New England and you just were to cut it right down, 400 miles, you would see all of these terrains represented in cross section. So interesting stuff. This is just if you go back to this, and let's just say we're looking at this belt right here. Well, that belt right here is represented right in here. So basically you have, if you were to look at the blue over here would be represented by this blue right here. If you were to look at the row belt, the row belt is in here. Go back. The Iapetus Ocean is after the row belt, which is represented here. That's the ocean sediments. We go to here, the Shelburne Falls Arc. That is represented here. We go to the actual Ganderia terrain. That is represented here. And the Rheic Ocean is right here. So we have actually Ganderia is kind of here, and then we have the Rheic Ocean here, and we have the Iapetus Ocean here. If I'm correct. I think I'm correct. Yeah. I'm going to go back to that. So let's see. So, yeah. Ocean sediments here, ocean sediments here. We have North America. We have the Mooretown right here. I believe Bronson Hill, and Shelburne. Yeah, those are right here. And then behind that, you have the Ganderia terrain with various island arcs in here and ocean sediments. All right. Anyway, it can get confusing, but this is really showing you how a cross section of what I just talked about. North America, island arc, closed ocean in gray, another island arc, closed ocean material here with island arcs inside, and then you have the Avalonia microcontinent right here. You have island arcs and volcanic arcs here that are associated from subduction going to the west. And then in these ocean sediments here and these in the Ganderia terrain, what you have are huge plutons that are injected in this, and this kind of stitches all this up right here. So Ganderia right here, you've got the arcs with it, you got the closure, you got an ocean closure right here, and this would be the Iapetus Ocean, and then you, of course, you have the, I'm sorry, this is the Rheic Ocean, and this is the Iapetus Ocean over here. And on this one, we are looking, okay, so we've got the row right here, the wrenches here, which is represented here, row here, Mooretown is here, this lighter green. This comes over, and they slam into each other, and then you got contact at like 465. Here, the island arc is now smashed together. Subduction has actually started off to the west, and that is represented by this right here. And then here's Ganderia is this part right here, and between Ganderia and this arc here is this area right here, and this right here is represented by that. That is the ocean, and this is going to crunch, and it's going to slam these and thrust and fault all these and compress them and make metamorphic rocks. And that is represented here. This is Ganderia. This is the arcs, Iapetus, Rheic, Ganderia right here, and then Avalon is right here. And this right here, this subduction right here is what's causing all this plutonic activity here, as Avalonia, this chunk here, which is represented here, gets slammed into here. So a little more simple of a diagram, but it explains a lot. And again, so you look at these two pieces here, they are represented by this area right here. The Mooretown is the front end right here. This closes, there's a COA in here, and then you have another island arc that forms right here, and this closes the Taconic Seaway. This closes the Iapetus Ocean, and then behind that is behind Avalonia is the is Africa. That will end up colliding with it. Yeah. Fascinating. These are where we got the ages, and how we were able to figure out all this, how all this occurred. Each of these dots represent ages, so these plutonic activity occurred over almost 100 million years, and these ages of these rocks, these volcanic rocks, are how we were able to figure out when these when these were formed, and when we know that when they were attached. That's how if we can get the age of that, that's how we know when the attachment occurred. You just have to find the rocks that were associated with the actual accretion of the island arc. So obviously these you would expect to be older because this part got welded on first, and bang, they are older. And then these over here would be younger than this over here, and they are. They're not always, because plutonic activity extends over a long period. And of course, the ones over here are even older. So this follows exactly what we'd feel. You would have, this was here before, this got slammed into it, the seaway got crunched, you had another island arc slam into it, into North America, and then you have the closure of the Iapetus. And then you have the Ganderia terrain crunched onto that. And then behind that, you have the microcontinent of Avalonia. And what likely happened, one of the reasons that we kind of know that these are more or less oceanic is they still exist. See, that the Rheic Ocean behind here, you don't see it between these two pieces because it got subducted underneath underneath the continent because it was heavier. So when you have continental material against oceanic material, continent always wins, and so that ends up staying left over. That's why we don't see really much of the Rheic Ocean. These are just tectonic terrains. Unless you really have a sharp eye, you're not really seeing much. But what we're looking at here is these are more or less, these are the Appalachian area right here. You have a piece of the Grenville basement here, basement rock here, Taconic rock up here of the Canadian Shield. And this is just giving you some ages and show you the different terrains. This is Avalonia here. It actually continues up through here. That's Meguma. You have Ganderia, which is sort of more or less this pink stuff right here. You have the Taconics, which are back here from the Taconic Orogeny. And then you have arc here, and arc here, and arc here. And then you have the coastal arc of Maine right here, and in between the Iapetus Ocean. That was interesting. Why'd that do that? Well, that's funny. This is, oh, because I outlined this. I put this in here to outline the Taconic Orogeny. Yeah, there's your Taconic Orogeny right there. That's area of deformation. New England tectonic terrains. Here we go. So now Laurentia. You have the Island Arc, the Roe Hill right here, Bronson Hill right here. You have what we refer to as the central. Oh, I can't think of that abbreviation. I have to look it up. This is Avalonia, but anyways, this right here would be more or less Ganderia, this area that occupies right here. That is the central Maine trough, that's what that is. And that is the maritime trough. And those are very common in front of subduction zones that are being subducted underneath continental material. And so that's why we have these are called troughs. They filled up with sediments as they were being from the closure of the Iapetus Ocean, and as they did, as this was going under, as this plate, this used to be the Iapetus Ocean, as this was going underneath the Bronson Hill Arc and the Roe Hill Arc and Laurentia, when you subduct under something, you have a tendency to drag it with you, and think about what's offshore. It's almost like a trench. I guess you could think of it like a trench, more or less. You know, every subduction zone has a trench. This is the trench material right here that filled up. And then this is the microcontinent of Avalonia, and then the Meguma. But within this trough, though, you do have this material is a mixture of microcontinent and oceanic, but we call it the Ganderia terrain because it's not nearly as it's not a true continental piece like this one is here. It just has pieces of it. All right, so here is the Taconic Orogeny as we just discussed. You know, short version of it, you have subduction this way. As it was subducting, you opened up the Taconic Seaway, and then everything kind of came crashing back onto it and lifted up over here. And then once the island arc hit, then the subduction began to switch gears and go underneath North America as opposed to going off of North America. It started coming towards it, and when that happened, we started to get plutonic activity coming up under here. But the Taconic Seaway was here. It is now gone. The island arc has been thrust up on here. We now have a subduction zone coming towards Laurentia. We do have a little bit of an opening up here, but this is going to end up drawing over, it's going to end up closing the Iapetus Ocean. This is just a geologic map of Maine showing the various terrains. This line, if you can kind of see that right there, it's what we refer to as the Nuremberger Fall. And the Nuremberger Fall, not to be confused with Ooga Booga, remember that old joke. This line acted very much like the San Andreas Fault about 380 million years ago. We had a lot of pressure coming this way, meaning that this kind of went this way and this was going this way. And that's why the terrains are so different. This is actual, what we call the coastal volcanic belt. Lots of plutonic activity during the Devonian, represented by these blobs right here. Acadia National Park is essentially a volcanic chamber. And this area here is radically different than what we call the central Maine trough. And this is the majority of this area here is ocean sediments. This is a volcanic arc. These are ocean sediments that were basically piled into a trench as this island arc right here was getting subducted as oceanic crust was going. There was another arc, there's an arc right here where subduction was going under here, and there was another one back here where subduction was going under here. And all of these right here, all of these are successions of belts that collided into North America. As I said, the Taconic was first. It's kind of off the chart right here, and then we had the Roe Hill, and then the Bronson Hill, and this is called the, I think, the Hurricane Ridge or the Lobster Anticline or something like that. But anyways, this is a row of mountains. Katahdin's right here, Sugarloaf, Saddleback, Bethel's right here. And this is a mountain range that was built from an arc that slammed onto this. And it's really, the mountains were much bigger. What we're seeing is basically the guts or the plutons that were injected into it. The mountains have been long gone. This is an interesting little area here. This is actually twice as old as this area here or here. And this is this is Proterozoic material that we think got punched up for one reason or another during one of the collisions of the island arcs. And right in here, actually, is a piece of Iapetus ocean crust that has been thrown up over it called an ufulite. And this is absolutely fascinating because you get a good look at what the ocean crust all the way down, you know, miles looks like. You get a good chunk of it. It went right up along this area right here. So that's for another discussion. And this is sort of the generalized area. You got island arc here, island arc here. You've got the closure of an ocean here, and these are ocean materials. The arc closed behind it, and then you have all of this ocean material here of the Iapetus Ocean, and then the volcanic belt island arc here, and then you have Avalonia that came behind it, and you have sections and pieces of Ganderia here. So North America island arc, closed ocean basin, island arc, closed ocean basin, pieces of continental material from Amazonia, island arc here, and then Avalonia right here. So somewhere in between here, there's probably some sort of a closure of, there's probably some ocean sediments here. We just can't see them. So yeah, and then you have all the plutonic activity that occurred underneath that volcanic island arc. As we move on to the Ordovician period, we are now at 458 million years ago. What we're looking at here is we are noticing the Iapetus Ocean is beginning to close. We have subduction off to the way down to the south on the other side of the ocean, ripping down. Basically, it's going straight south. If we were in current position, it would be straight east. But what is happening is pieces of continental material down here are being rifted off because of the subduction offshore. And so you got your Avalonia here, the Ganderia terrain here, and this is going to end up getting pulled across over here. This arc right here is the Taconic. Here is Maine. At this point, the Taconic has now arrived. Subduction is this way. The island arc has been blasted in here. And what's going to happen now is we're going to shift gears and we're going to bring these pieces over here as well. Baltica is going to end up going, I believe, straight up to the, in this position, it would be to the north-northwest. And it's going to collide with offshore of Greenland. And then eventually this area here is going to, this is Gondwana, and this is going to end up coming over and slamming into the east coast and closing the Iapetus Ocean. But this has a long way to go. It's got to come down here, up and around. And it's interesting because you're seeing pieces of this, and it looks like it's so far away, but believe it or not, the pieces of this area here, and how's this do this? This orientation isn't right for it. But eventually, this map may not be 100% correct as far as this down here goes. So we're going to take that with a grain of salt, because I know well, the current pieces of this have come off of over here, but maybe that happened much earlier. Um, but this map is not making the sense to me. This rift, this arc right here makes sense, because this is pulling in the Taconic. New England and Nova Scotia being down here, that is correct, but it should be coming off of, oh, you know what, maybe it's coming off of this down here. Yeah, that's what it is. Okay, this was, these extend down here, it's just skewed, but that's what happened. Believe it or not, this actually continues down here, as well as the part of Africa, and these pieces were ripped off somewhere down in here. Actually, we know that because some of the REEs and the zircons and the properties tell us that this was originally in a very cold area when it ripped it off. So this is the Ordovician period. Ordovician this is the island arc right here of the Taconic Mountains, and they are going to slam in and close the Taconic Seaway. Here is Maine right here. This is Laurentia. As we can tell, sea level is much higher. It's flooding a good portion of this, the Great Plains. North America on the west coast isn't even there. There's a basin up here in what will eventually become the Arctic Ocean. But the continent floods often, especially through the Paleozoic. And this is just a time of higher sea level, probably because of the amount of spreading centers. There seems to be a correlation between the amount of spreading centers, like mid-ocean ridges, and the amount of how high sea level is. You have more spreading centers, that means that there's more magma being pushed through the Earth's crust, which means that the spreading centers are lifting. The actual floor of the ocean is lifting, which means you're displacing water, which means it needs some place to go, and it raises sea level. This is the Ordovician 470, and now we are closing the Taconic Seaway, and this is the Green Mountains being built, and bang, they have now a hit, and they are now being thrusted up onto North America, and oddly enough, now a trough is beginning to develop here, and this is a subduction starting to form to the west. Right back here, we have some microcontinents. We have Ganderia, and then this is likely part of Avalonia. So here we are, Ordovician tectonic and paleogeographic map 460 million years ago. We are right here. The Taconic Green Mountains have been built. Subduction has stopped, and we now have an island arc. More material being drawn into North America. So sediments on the bottom of the ocean have been compressed, uplifted, and are now thrust up against Laurentia. So this piece here is this piece here, and these sediments right here are this right here, and that is what makes up a good chunk of the Green Mountains. And that's represented by this little circle here. So we've got a trench offshore, which is where this stuff piled up. We have the Taconic Mountains that have built here, and they are dumping materials into this area right here. The Taconic Mountains are right here, and they're dumping material into this area here, which would be basically right in here on the next slide. On the timeline chart, this is where we are. The Taconic Seaway has closed. The Taconic Mountains are being built, and we are now moving on. This is what eastern Vermont may have looked like 460 million years ago. We have the Taconic Mountains. There's an inland sea. There is offshore island arcs. You have this wouldn't really be considered Baltica. This is just an island arc, so just take that. I just use this. This kind of gives you an idea of what we're looking at, though. This is going to end up being thrust up on here more. You have this is a huge area of reef where life really got its chance to begin. Very clear water, spectacular water. Again, very much like the Maldives or the Bahamas or Indonesia. Just beautiful water. You got an offshore arc, and this is going to continue to get thrust up onto here. And we already went through this. This is just rehashing the cross-section of the Taconic Orogeny events. Vermont arc, offshore island arc, gets thrust up onto Laurentia, and boom, you have the Green Mountains. This is kind of what it would have looked like maybe if you were to show up in 450 million years ago, take a good look and plop down in what is now, I don't know, Montpelier, J Peak, whatever. But you might see something that looks like this offshore. Or maybe that area would have been just like this right now. I mean, there's definitely subduction off of the coast of here that has built this island arc, and this mountain range is being slammed up against a continent. So, well, not yet, but eventually will be. This would be an excellent example of an island arc offshore of that was going to make the Taconic Mountains for sure. And New England, 480 million years ago. This is Lombok, Indonesia. You have volcanics. You have a very warm tropical ocean, probably plenty of waves. You have very rocky, mountainous island arcs coming straight into the ocean. Sometimes they have, caustic sediments, sediments being eroded from the mountains. Otherwise, it's actual volcanoes themselves coming right out. So, but this is kind of an idea of what it might have looked like. Vermont Mountains, here is that's Camel's Hump, I believe. Probably looking at it towards the, well, north is definitely this way over here, because this has been scraped off by glaciers. But this is a great example of I believe that's I'm not sure exactly what the actual hump is made out of, but it's definitely something resistant. It's probably gneiss or schist at the very least. I don't believe it is granitic. Most of the high peaks in Vermont are high-level, high metamorphosed schist. So I think that's what it is. But these are really ocean sediments that were compressed, crunched, buried, and heated, and just heated to a point where they form very resistant ridges. But the mountains that were originally here were at least another 10,000 feet above this. So you're looking at the guts. You're just seeing you're looking at what was about 6 miles down. Yep, there's a hump. Well, looking at that could be igneous. I'm not sure. It looks like it's exfoliating, but I'd have to do some more work on that. So in the Ordovician, plants are beginning to well, they're going to start. For the most part, we didn't think they started happening until the Devonian, the Silurian, which is after this period. But we do think now it's began a little bit earlier, and really it just had something to do with cyanobacteria or whatever. Trying to make a gun for the once they started figuring out how they could survive on land, or how they could survive without the water, they moved on land, and that is this is a big step, because prior to this the land was barren. So Silurian period, 425 million years ago, we have subduction going under North America. We have Avalonia right here. The Iapetus Ocean is closing. You have the Rheic Ocean behind it, and North America is largely flooded. We had very high sea levels during this time, but this is becoming the end of the Iapetus Ocean, and really we're closing. This is becoming the end of a Wilson cycle. North America is about to go under a huge mountain building episode on the East Coast. We have the Taconics right here above sea level, but here's Avalonia, and things are really going to start to crank up. We have Baltica here, which is Europe, which is now collided with Greenland. So you're going to form a mountain range in Norway, northern Baltica, which is again Europe, and then the east coast of Greenland. So Norway, Finland, these are all the mountains that are built during that, and that happens about 425 million years ago. And what's going to happen is this this ocean is just going to close up like a zipper. So it's going to start closing from north to south. And then this piece is going to slam onto us right here, North America in the northeast, and it's actually going to start to be driven along the coast slightly. So that's why we get that transform fault, that lateral fault, the Norimboga Fault in Maine. This is a piece of this that is actually starts sliding down, and it takes pieces of crust with it. So subduction underneath North America. You've got subduction underneath the west coast of Africa, and you have an ocean that's now formed between the two called the Rheic Ocean. You have the Iapetus would be here, and this is the northern part of it closing, and then you have the Rheic behind it. Technically, this is still the Iapetus down here, but for our purposes, this whole thing is closing up. This will be first, and then this behind it, and then all of this comes into North America. Silurian period, Taconic highlands are now hit. We have more action coming behind us. This is Baltica coming in and closing part of the Iapetus Ocean to the north. And again, this is just going to close like a zipper. These are part of Avalonia, and this whole thing this is going to be the Caledonian mountain range. This is Finland and Norway. Microcontinents are going to slam into this, build our mountains here, and then these are going to slam in and build in the south, and this slams into the southeastern part of the United States. And like I said, it's like one big zipper, and of course here's Maine. And now the northern Iapetus is closed, or just this part of the Iapetus is closed. Baltica, Europe, rather, Maine, microcontinents getting slammed into or island arcs, more arcs getting slammed into North America. Maine is starting to look very rippled and mountainous here because this whole thing is beginning to stitch up, and again, this is going to zip up right down here. So here we are, Silurian tectonic and paleogeographic map. Grenville came, Grenville went. Island arc that built the Green Mountains came, slammed. We now have the Taconic Mountains. We have more crust coming over in the form of Ganderia. That is going on its way over. That has come. That is crushed. All right, or has not crushed it. I'm sorry, but it's on its way. So we have two pieces of subduction right here. We have subducting under North America. We have subducting under Ganderia. We have a new ocean that's opened up right here, and this area right here is an area that was this is Africa here. I'm sorry, this is not Africa. This is just another piece of microcontinent here. But in any case, this piece here, this was torn off of northwestern, either northwestern Africa or Amazonia. In that time, it created an ocean basin behind it, and as it did, it began to fill with sediments as well. And so, are we calling that Africa? We are calling that Avalonia. Huh. You know, I think that for all intents and purposes, actually, we're going to stick with that. This would have been Ganderia. This would have been Avalonia. And these two pieces are represented by these two pieces here. So that does make sense. So what's going to happen is this piece here is going to get this ocean right here. This is the Iapetus, or not the Iapetus, but part of it is going to close, and behind it is going to be another basin that opens up, and behind that, if this is truly Avalonia right here, which I believe it is, yes, it is, because this piece is this piece is this piece, this piece is this piece, and then there's Africa. So this is just a series of another small basin that opens up, or a trough, and that gets filled, probably from back arc, spreading from this subduction right here, and this eventually will run into, this is eventually going to go here, this is going to go here, both of these are going to weld together, and then Africa is going to come behind it. So Ganderia, Avalonia, and then once Avalonia hits, then we have nothing left but the Rheic Ocean behind it, which is going to be closed by Africa. So that's where we are. And this brings us to the first thing I can mention about the marginal way, that the marginal way is made in these sediments right here. So somewhere between here, Ganderia and Amazon, I mean, and Avalonia, you have an area that where sediments piled up, and bingo, this is where we find our sediments in the marginal way. And so we've got a trench, open ocean, mountain range, inland sea here. Got carbonates, beautiful warm water. Life is really, out here it's probably doing just fine. You got some deep marine here. But basically you've got a mountain building episode right here and a very large trench because the Iapetus Ocean is closing. So subduction reversal in the late Silurian. So we've got, this is basically the coastal, this is called the Falmouth-Brunswick Island Arc. And so this would be northwestern Maine, this would be central Maine, this would be the coastal arc, and then this would be more or less the eastern part of the ocean. So you've got North America, you've got a seaway here, you've got the island arc, and then you've got more ocean over here. And what's happening is this piece of subduction, this crust is now going under here. It's melting, producing an arc. The arc is producing sediments that are going here and sediments that are going here. And what's eventually going to happen is this is going to go over here and slam into, and it's going to crunch, and it's going to suck these sediments down. It's going to deform these sediments here, and eventually this slab is going to break off as this occurs. And when this does happen, you're going to get a rebound effect, and then subduction, for one reason or another, decides to switch directions, probably more so because once this contacts this, it has no place to go, and then the slab breaks off, subduction reverses and starts going west and begins to drag this piece over here into this here. And what ends up happening is this piece goes under, this piece goes under this whole piece here, and everything gets this piece of microcontinent here gets dragged, and everything that was in the ocean bottom here gets thrust up over it like that in the form of thrust faults. And so these sediments that were deposited on the western side of that arc, which we kind of know as more or less the central Maine trough, are essentially these sediments right in here and here that have been thrust up. So you had sediments on the west side of the trough, you had sediments on the east, on the arc, and you had sediments on the east side of the arc, and then the arc ends up eroding, the slab breaks off, and then subduction reverses, and then all of this stuff here gets thrust up on here because this gets drilled this way, and this is represented right here by all the deformation. And when you go across the central Maine belts, you see these different layers and different degrees of metamorphism. So it's interesting to check that out. You can see pieces of the arc that have been thrust up on top of each other. You can see pieces of ocean bottom that have been metamorphosed and created into slates and schist. And what's interesting is there are places where you can tell in the central Maine trough whether or not the sediments were derivative of North America or they're a derivative of the microcontinent. And that's been an area of a lot of research, because we kind of think that west of, let's just say, the Mount Washington range, from what we can tell, was pretty much deposited from sediments that came from the east. So more likely Avalonia or the Ganderia subcontinent were, or just maybe an island arc offshore, but we kind of think that the sediments of at least to Mount Washington came from the east. And then behind that, sediments came from the west, and there is some overlap. So I think that one of the famous formations in the Mount Washington area is the Littleton Formation. And if you want to read up about it, it will tell you, which I've read up on. I think the Littleton may have been an East Coast derived, an Eastern derived sediment source. But when you look at Mount Washington, you can certainly see that the beds dip, the sedimentary beds dip to the west. So that means that they were piling on from the east. So that's kind of interesting. All right, Silurian landscape here. We've got some plants that are starting to come in. You know, atmosphere is still, you know, there's more oxygen. It's beginning to look a little bit more familiar. No animals though. Late Silurian landscape here. Plants are beginning to really spruce it up a little bit. You're starting to see some mountains. Yeah, it's starting to look more like the Earth that we know. All right, now we move on to the Devonian period, and this is when it really happens for, this is our period. The Devonian and the Carboniferous is what really makes Maine. Maine, New Hampshire, Vermont, Nova Scotia, all of it. So what's going on here? Early Devonian. The Iapetus is gone. It's been subducted. The Rheic Ocean behind, this is Avalonia, right in here. Avalonia has now been, is now suturing on to North America. Through westward dipping subduction. The ocean behind it, the Rheic Ocean, is now beginning to close, and Gondwana, that consists of Africa and South America and everything else besides really North America and Siberia, is going to slam into the east coast of North America, closing the ocean, completing the Wilson cycle, and making a mountain range that is probably bigger than the Himalayas. So we have Avalonian stuff over here, pieces of island arcs, Ganderia, slamming in. Here is Maine. We have now zippered down. The Iapetus Ocean is essentially zippering down, and then we have right back here would be the Rheic Ocean, and these are gonna finally slam into here and finish the job of making the majority of Maine's mountains. And in fact, over the next 100 million years, all of this is just going to crunch up and build a gigantic mountain range. Which of these pieces is actually Avalonia? I'm not 100% sure. I'm not sure if it's already here. I don't think it is, but I think it's right back here. 435, yes. These are the final pieces. Everything is going to get slammed. There's a nice giant trough in front of it, and this is going to be, these are the Ganderia trains, and the trough is going to be filled with sediments in front of, in between Ganderia and Avalonia, and this creates, you know, the majority of the central Maine basin. 360, we now have contact. Huge deep troughs right here that are going to fill with sediment. We do not get a chance to really see these anywhere in New England. These are more offshore. Parts of Nova Scotia do have it, but this is going to be the end. It's coming up here. The closure of this is the Rheic Ocean. Here's Maine, just located in the, I mean, if you were here now, you would just start to see some very, very large mountains. So here's what we got going on. Avalonia was here. Ganderia is here. The eastern Iapetus was here. This is here. This is here. Africa is now closing. Africa is now closing in on North America, and we are closing the remaining part. This is the Rheic Ocean right here, which would have been behind here. So now we are here. This is the end result. So we have mountains right here, giant mountain range here. We have you know, lowlands and, you know, plains being eroded, and this is all material that's coming from here, which is eventually going here. We have some shallow marine inland sea here, and then some deeper stuff here, and a very deep trench right over here. All right, here we are on the time chart. Acadian orogeny, about 360 million years ago. Iapetus, Taconic Seaway gone, check. Iapetus Ocean gone. And we have some, basically this is means things are moving, sort of uh, parallel to the coast of New England when you see these right here, one of these being the Nuremberger Fault. And now we're about to close the Rheic Ocean, because the Rheic Ocean is what formed behind Avalonia when it separated off of northern Africa. Oop. The Acadian Orogeny. All right. The Acadian Orogeny is essentially what built, excuse me, the guts of Maine and New Hampshire, Eastern Mass, Rhode Island, pretty much everything east of central Vermont. I'm sorry, pretty much everything east of central Vermont, Western Mass, Western Connecticut is involved in this orogeny. And it kind of goes like this. You have exotic terrain, Meguma here. You have Avalonia here. This is an exotic terrain off of northern Africa. Not 100% where Meguma comes from, probably somewhere in the same area. You have this area here. Pieces of this were ripped off of northeastern Amazonia. And then you have this trough in here. These are both, you've got ocean sediments, the closing of the Iapetus Ocean recorded here. You got the Conic Seaway close it here. You got some arcs right out here. But this is what we're going to do right here. So Laurentia, you have basically, for all intents and purposes, this would be more or less Vermont, or if you're in Maine, it would be, to the northwest, it would be Canada. You have subduction going underneath North America. You have subduction going underneath island arcs that are out here. So stuff's being blasted up into here, blasted up into here. You have an island arc, and you have Ganderia closing in on all of this. At 430 million years ago, this subduction has stopped here. The Popo has been slammed onto North America. So you've got Laurentia, you've got the Mooretown, you've got the Popo, you've got another arc right here. Or actually, these are just sediments that are forming in the trough behind the Popo arc. You have the Frederickson trough. This is just another trough within the. You're not seeing it here. They're just little areas within this actual belt. Like I can make stripes going like this, and that would represent this. And then the next amount of sediments, the blue right here. So here's the Ganderia terrain right here. It is now about to slam into North America and deform and compress all of these. At 415 million years ago, Ganderia has now accreted onto North America. It has compressed the Frederickson terrain. It has compressed the LO belt, the Pope arc, the Mooretown, and Laurentia. And guarantee you, it has deformed all of this. You have slab break off here, which means you're going to have volcanic intrusions going here. You have a slab of ocean, which was once. This is the Iapetus. This is the Rheic. I'm sorry. No, this is the other. This is the western Iapetus. This is the eastern Iapetus. Avalonia is now going to slam into where behind Ganderia. You're going to make the volcanic belt along the coast of Maine. So you have Avalonia, which is offshore of Maine. You have the volcanic belt, which is like Wiscasset. You have Ganderia, which is the central volcanic. This is the trough right here. So Avalonia, boom. You have the coastal volcanic belt, which runs right up here. You have Ganderia, which is this whole area right here. You have the LO, you have the Popak Arc, you have the Mooretown. That is all this back here. And then you have Laurentia, which is here. At 395 million years ago, it is all pretty much said and done. Meguma. And this break right here is basically saying that we don't really know what's going on with the relationship between these two. So we're still kind of working. We don't know the time period on that when Meguma came over. Meguma could be oceanic sediments. I'm not 100% sure. I believe it's a piece of microcontinent. Not 100% though. Or it could be like a Ganderia terrain. It could just be a mixture. In any case, Any case, the final stage of this is 395 million years ago. You have Laurentia, which is you have Laurentia, which has the Mooretown terrain accreted onto it, which has the Popo arc, volcanic arc welded onto it. You have sediments within the LO belt. You have the Fredericton Trough sediments compressed and thrust. You have Ganderia thrust underneath that. You have Avalonia going underneath Ganderia, or trying to, but it more or less stops. You have slab break off here, which is going to produce massive amounts of plutonism here. You have Meguma eventually attached to Avalonia, and then you have Gondwana at some other point, which will somewhere in the next around 300 million years, Gondwana connects. So Meguma maybe around 395. I think Gondwana about 3. It's around 3. But in any case, maybe even later than that. I forget when Africa actually makes contact. But anyways, this is a cross section of this, and this is how this area here formed. Depositional environment on the Devonian. All right, so this is, I'm going to stop here and take a break because now we're getting into the sediments that make up the marginal way.